Welcome. If you're here, chances are you're looking for something a little different tonight. Not noise, not urgency, just something quiet and interesting to carry you towards sleep. That's exactly what this is. Over the next 2 hours or so, we're going to take a calm, unhurried journey through one of the most remarkable stories in human history. The story of military aviation. From the very beginning, when pilots climbed into wooden frames held together with wire and flew over the battlefields of the First World War, all the way through to the stealth aircraft and autonomous drones of the present day. Each chapter moves gently through a different era. The facts are real, the history is genuine, and the pace is designed for exactly this. For lying down, for letting your mind wander, for drifting in and out as the story unfolds around you. There's nothing you need to remember, nothing you need to study, just a long, quiet, fascinating story told slowly in the dark for you. If you enjoy this kind of content, please do consider leaving a like and subscribing to the channel. It genuinely helps more people find their way here, and it allows us to keep making these long, restful journeys for you. A simple click means more than you might think. Thank you for being here. Thank you for choosing to spend your evening, or your night, or your early hours in this company. Now, get comfortable. Let your body settle. Let the day go. The sky is waiting. Chapter 1: World War I, the First War in the Sky. Before radar, before metal wings, before speed records, there were wooden frames stretched with fabric, held together by wire and hope. Pilots climbed into open cockpits with nothing but goggles and courage. The sky was new territory, and for the first time in history, war followed humanity into the air. Tonight, we begin where military aviation began. Slow, fragile, and uncertain. Take a breath. Let your body settle. Whatever the day brought you, it belongs to the past now. There's nothing you need to do, nowhere you need to be, just the quiet story of how human beings first learned to fight in the sky. We're going back to 1914. The fields of Europe stretch out below, and above them, for the very first time, soldiers are climbing into the air. The earliest military aircraft had one simple, humble purpose. They were eyes. Not weapons, not machines of destruction, just eyes. When the First World War began, the generals who ran armies were accustomed to the old rhythms of ground warfare. You sent scouts on horseback. You climbed a hill. You pressed your binoculars to your eyes and tried to see what was on the other side of a ridge. But the scale of this new war was enormous. Trenches stretched for hundreds of miles. Information was everything. And so, military commanders began to use aircraft for reconnaissance. A pilot would take off from a grass field behind the lines, fly low over enemy territory, and observe troop positions, supply routes, artillery placements. These were not men sitting behind instrument panels in pressurized cabins. These were human beings clinging to open wooden frames, exposed to the sky in every direction, carrying nothing but their own eyesight and whatever notes they could scratch down in the rattling, shaking air. Rest your shoulders. Let them drop a little. Just let the thoughts move through like clouds. Those early pilots flew without parachutes, not because parachutes didn't exist. Balloon observers during the war were often equipped with them, but aircraft pilots, by and large, were not. There were senior officers who worried that giving pilots parachutes would encourage them to abandon their aircraft too readily. Whether you find that reasoning understandable or troubling depends on where you're standing. What is not in question is the consequence. When fire broke out in a canvas and wood machine soaked in fuel, pilots had almost no options. The life expectancy of a new pilot at the front in certain periods of the war could be measured in weeks. These were very young men, and they flew without nets. The aircraft themselves were built from wood and fabric and wire. Frames of spruce or ash, stretched with linen coated in lacquer that tightened and stiffened the material. Bracing wires ran between the wings and the fuselage, holding everything in tension. The whole thing was in a kind of conversation with itself, each element depending on the others. It was elegant in its way, but also fragile. Fabric could tear, wood could crack. A tracer round, or simply the stress of a dive, could compromise a structure in seconds. And then there was the cold. Open cockpits meant open air. At altitude, the temperature dropped sharply, even in summer. Pilots wore layers of leather and wool, but no amount of clothing could fully insulate a person sitting in what was essentially a hole in a wooden frame, moving at 60 or 70 miles an hour through unprotected sky. Frostbite, frozen goggles, controls that could stiffen, oil that could thicken, and yet pilots flew. Some flew multiple sorties in a single day. They climbed out, warmed their hands around something hot, and climbed back in. Breathe slowly. The night is long and quiet, and you are exactly where you should be. Both sides were flying now, and it didn't take long before the obvious question arose. How do you stop them? The earliest answer was improvised. Pilots took pistols into the air, rifles. There are accounts of pilots throwing bricks and grappling hooks. None of it was particularly effective, and yet the impulse was undeniable. Here was the enemy, right there, close enough sometimes to make eye contact. What was needed was a machine gun that could fire forward. But forward meant through the propeller arc. Fire without some kind of management, and you'd destroy your own propeller immediately. A Dutch designer named Anthony Fokker solved it. His team developed a mechanical interrupter gear that synchronized the machine gun's firing cycle to the rotation of the propeller. The gun fired only when no blade was in the way. Precise, elegant, deadly. Fitted to the Fokker Eindecker, this system transformed aerial combat. German pilots suddenly had a purpose-built fighting machine that could point its nose at an enemy and fire with devastating accuracy. The period that followed became known to Allied airmen as the Fokker Scourge. German aircraft dominated the skies for months. Let your eyelids be heavy if they want to be. Let the images come softly, like old photographs fading at the edges. The Allies caught up. They always did. And one of the machines that helped restore the balance was British. The Sopwith Camel. Compact and powerful, with twin synchronized machine guns and extraordinary maneuverability. The Camel became one of the most significant fighter aircraft of the entire war. It was also notoriously difficult to fly. The gyroscopic effect of its rotary engine gave it handling characteristics that could surprise and punish the inexperienced. It would turn sharply one way with great speed, and the other way with great reluctance. But in the right hands, it was devastating. It has been credited with more aerial victories than any other Allied aircraft of the war. The men who flew it well loved it, with the complicated love that comes from mastering something genuinely difficult. Designers were also experimenting with the triplane, 3 wings instead of 2, more lift, better climb, tighter turns. The most famous was German, the Fokker DR-1, flown by Manfred von Richthofen, the Red Baron, the war's highest-scoring ace. The triplane had real virtues, but the extra wing added weight and drag, and the era was brief. By the war's end, most air forces were moving back toward refined biplanes, or beginning to imagine something new entirely. And all of this happened within reach of the ground. The airfields of the First World War were not vast paved installations. They were grass strips near the front lines. A few wooden hangars, mechanics working outdoors in all weathers. The sound of artillery, never far away. There was a particular culture in those airfields, a refusal to dwell on what might happen, a brightness, an intensity of living in the present moment, meals eaten with appetite, laughter that might seem strange to an outsider, but made complete sense to the people sharing it. They were very young. They were doing something no generation before them had ever done, and they did it every morning, climbing into fragile wooden aircraft and taking the sky. Let your mind rest in that image now. A quiet field, early morning, dew on the grass, an engine warming up somewhere in the distance. Watch the aircraft move slowly across the wet grass, and then faster, and then lift, impossibly it seems, and yet completely naturally, into the pale morning air. Watch it climb. Watch it grow smaller against the sky, and let your own body grow heavier, more settled with each moment it rises. The war in the sky had begun, and the world would never see the sky the same way again. Sleep now, gently, just the quiet sky, just the beginning of things. Chapter 2: World War II, Speed, Range, and Power. 2 decades later, the sky had changed. Wood gave way to aluminum. Open cockpits became sealed canopies. Engines roared louder. Air power was no longer experimental. It had become decisive. Across oceans and continents, aircraft reshaped strategy, distance, and possibility. The war in the sky had matured. Let your body settle. Let the day go quiet behind you. We're moving forward now, 20 years on from the grass fields and the wire bracing. The world has changed, and the sky above it has changed with it. It's 1939, and everything is about to get louder. The most visible change between the wars was the one you could see from a distance. The aircraft themselves looked different, felt different, were fundamentally different in what they were made of. Wood and fabric had defined the First World War. They were the materials available, the materials understood, the materials that could be worked by hand in a barn or a workshop. But they had limits. Limits of strength, limits of speed, limits of what you could ask a structure to endure. Aluminum changed that. Light, strong, and workable, aluminum alloy became the material of a new generation of aircraft. Where First World War machines had been assembled almost like furniture, with skilled hands shaping timber and stitching fabric, Second World War aircraft were engineered, designed with precision, manufactured at scale. The difference wasn't just in how they were built, it was in what they could do. All-metal construction allowed designers to push for speeds, ranges, and altitudes that fabric and wood could never have survived. The aircraft of the Second World War were not refinements of what came before. They were a different kind of machine entirely. Breathe slowly. There's nothing to hold on to. Just the story, moving gently forward. Inside those metal airframes, pilots sat in a different world too. The open cockpit, which had been simply the way things were done in the First World War, was gone. In its place, enclosed canopies of shaped perspex gave pilots protection from the wind, from the cold, from the physical punishment of high-speed flight. A pilot who had flown in 1917 would have recognized the controls and the instruments. But the experience of sitting inside a sealed, streamlined machine, traveling at 300 or 400 miles an hour, was something entirely new. It wasn't just comfort. Though comfort mattered, enclosed cockpits changed what pilots could do. At high altitude, where temperatures could plunge far below anything the leather and wool of an earlier era could manage, a sealed cockpit meant the difference between a pilot who could function and one who could not. And a pilot who could function, who could think clearly and react quickly and fly with precision, was the whole point. One aircraft above all others came to represent Britain's experience of that war, the Supermarine Spitfire. There is something about the Spitfire that goes beyond its technical specifications, though those were remarkable enough. The elliptical wings, the narrow nose, the sound of the Merlin engine, a sound that people who heard it in the summer of 1940 never forgot for the rest of their lives. The Spitfire was fast. It was agile. It was beautiful in the particular way that things designed to do one thing very well often are. And it arrived at exactly the moment Britain needed it most. During the Battle of Britain, fought in the skies over southern England through the summer and autumn of 1940, the Spitfire and its companion the Hurricane faced the full weight of the German Luftwaffe. The outcome was not certain. There were days when the losses on both sides were severe enough that the result genuinely hung in the balance. But the battle was won, and the Spitfire, rightly or not, became the symbol of that winning. It was developed and improved continuously throughout the war. Engines grew more powerful, armament changed, the wings were modified. By the war's end, the Spitfire flying combat missions barely resembled the one that had entered service years earlier, except in spirit. Let your shoulders drop. Let the weight of the day finish leaving you. You're safe. You're resting. Just here in the quiet. On the other side of the Atlantic, American engineering was solving a different problem. By the middle years of the war, the Allied strategy in Europe depended heavily on strategic bombing. Long-range bombers, the B-17 Flying Fortress among them, were flying deep into occupied Europe and Germany itself, targeting factories, railroads, oil refineries. The theory was sound. The execution was costly. Bombers flying without fighter escort were vulnerable. They flew in tight formations for mutual protection, gunners covering every angle they could. But against determined fighter opposition, losses climbed to levels that were difficult to sustain. What was needed was a fighter that could accompany the bombers all the way, not just to the edge of its range, and then turn back, leaving the bombers alone for the most dangerous part of the mission, all the way there and all the way home. The P-51 Mustang, fitted with the same Rolls-Royce Merlin engine that powered the Spitfire, became that aircraft. With drop tanks that could be jettisoned when empty, the Mustang had a range that seemed almost implausible for a single-engine fighter. It could escort bombers deep into Germany, and when enemy fighters rose to intercept, it could fight them on equal terms. The effect on the air war over Europe was significant. Bomber losses fell. The pressure on German industry and infrastructure increased. The P-51 didn't win the war by itself, but it changed the arithmetic of the air campaign in ways that mattered enormously. Drift a little deeper now. Let your mind soften at the edges. While aircraft were transforming what was possible in the sky, a technology on the ground was transforming how those aircraft could be found, tracked, and fought. Radar had been developed in the years before the war by several nations more or less simultaneously. Britain, in particular, had built a chain of radar stations along its southern and eastern coasts, a system called Chain Home that could detect incoming aircraft at distances that gave fighter controllers precious minutes of warning. Those minutes mattered enormously. A fighter scrambling from the ground needs time to climb to altitude. Without radar, the warning might come too late. With it, Spitfires and Hurricanes could be vectored toward incoming German formations, with enough time to reach the right altitude and position for an effective interception. Radar didn't just change individual engagements. It changed the entire logic of air defense. For the first time, the sky was not simply invisible until an aircraft appeared overhead. It was watchable, monitorable. The defender had information, and information changed everything. Far out at sea, a different kind of transformation was underway. Aircraft carriers had existed since the First World War, but it was the Second World War that demonstrated what they could truly do. In the Pacific, where the distances involved made land-based air power insufficient for much of the fighting, the aircraft carrier became the dominant weapon of naval warfare. The attack on Pearl Harbor in December 1941 was launched entirely from carriers. The Battle of Midway, fought 6 months later, was decided by carrier-based aircraft striking at each other's fleets without the surface ships ever coming within sight of one another. The battleship, the symbol of naval power for generations, found itself secondary to a floating airfield that could project force across hundreds of miles of open ocean. It was a profound shift, and it pointed toward a future in which air power and sea power were no longer separate things. High above all of this, another quiet revolution was taking place. As aircraft flew higher, the thin air at extreme altitude created a new problem. Pilots needed oxygen, they needed warmth, and at the very highest operational altitudes, they needed something more. They needed pressurization. Pressurized cabins, which maintained breathable air pressure inside the aircraft, regardless of the altitude outside, began appearing in high-altitude bombers. The B-29 Superfortress, which flew missions over Japan from bases in the Pacific, operated at altitudes that earlier aircraft could never have reached with a functioning crew. The technology was complex and added weight and engineering challenges, but it opened the sky further upward into regions that had previously been unreachable in any sustained, practical way. And then, near the end, something appeared that pointed beyond everything else. Something that didn't belong to the world of propellers and piston engines at all. The Messerschmitt Me-262 entered operational service with the German Luftwaffe in 1944. It was the world's first operational jet-powered fighter aircraft. Its engines didn't spin a propeller. They pushed air through, burned fuel in it, and expelled it rearward with enough force to push the aircraft forward at speeds no piston-engined plane could match. Allied pilots who encountered it described something that felt fundamentally different. It was faster. It climbed differently. It moved through the sky with a quality that was hard to describe to someone who hadn't seen it. It came too late and in too few numbers to change the outcome of the war. Germany's situation by 1944 was already beyond saving by any single weapon. But the Me-262 was a message, a signal from the future that had arrived slightly ahead of schedule. The age of the jet was coming. Nothing after the war would ever quite be the same. That's where we rest tonight, in the moment just before everything changed again. The aluminum and the Merlin engines, the radar screens and the carrier decks, the pressurized cabins reaching toward the edge of the sky, and one strange, fast, improbable aircraft pointing toward something none of them could fully see yet. Let your breathing slow. Let the images soften and drift. The war is over. The sky is quiet. Sleep now, gently. Chapter 3. The Jet Age begins. Korea. Then, almost suddenly, the propellers disappeared. A new sound replaced them, a sharper roar, a smoother surge. Jets swept their wings backward and chased the edge of sound itself. Speed doubled, altitude climbed, time shrank. The sky felt smaller now and far more dangerous. Let yourself settle. Let the quiet find you. We're moving forward again, just a few years on from the end of the Second Great War. The world is tired, but the sky is restless. The jet age has arrived, and it arrived faster than almost anyone expected. The aircraft that came home from the Second World War were the finest piston-engined machines humanity had ever built. The Spitfire, the Mustang, the Corsair. They represented the absolute peak of a technology refined over 3 decades of increasingly urgent need. And within just a few years, almost all of them were obsolete. That is how quickly things moved. The jet engine, which had appeared so briefly and so dramatically in the final months of the war, was not a curiosity, it was a doorway. And once it opened, the engineers and designers who walked through it discovered that the old rules no longer applied in quite the same way. Piston engines pulled aircraft through the air with spinning propellers. Jets pushed them. The difference sounds simple. The consequences were profound. Speeds that had taken decades to achieve with propellers were surpassed in just a few years of jet development. The ceiling climbed. The performance envelope expanded in directions that would have seemed implausible to a pilot who had flown in 1945, let alone 1918. Breathe gently. There's nothing requiring your attention, just the story, unfolding slowly, carrying you forward. One of the first things the engineers discovered was that the shape of the wing mattered in ways that older, slower aircraft had never needed to account for. At the speeds jet engines were now making possible, a straight wing created problems. As an aircraft approached the speed of sound, the air flowing over a straight wing began to compress in ways that increased drag dramatically and made the aircraft difficult or impossible to control. The solution, arrived at through both theoretical work and captured German research from the end of the war. A swept wing delayed the onset of those compressibility effects. It allowed the aircraft to push closer to the speed of sound and eventually past it without losing control. It looked different from anything that had come before. Sleeker, more angular. more deliberately aggressive in its geometry. Swept wings became the defining visual feature of the new generation of jet fighters. And the aircraft that made them famous was a product of the first jet-on-jet war in history, Korea, 1950. When North Korean forces crossed the 38th parallel and the conflict began, the aircraft sent to respond were a mixture of late propeller types and early jets. Within months, the air war over Korea had become something genuinely new. A contest between jet aircraft flying at speeds and altitudes that made everything that had come before seem almost leisurely. Two aircraft came to define that contest: the American F-86 Sabre and the Soviet-designed MiG-15. Both were swept-wing jets. Both were fast, capable, and representative of the best their respective design traditions could produce. The MiG-15 had certain advantages. It climbed faster. It had a higher service ceiling. Its armament was heavier. The F-86 countered with superior handling at lower altitudes, and many pilots felt better overall controllability in a turning fight. The engagements between them fought mostly in a region of northwest Korea near the Chinese border that became known as MiG Alley, were the first sustained jet versus jet air combat in history. Pilots on both sides were learning new things almost every day. The tactics of propeller-era combat didn't translate perfectly. Speeds were different. The geometry of engagement was different. Everything had to be relearned in real time, in real danger. What emerged from those encounters shaped military aviation doctrine for the decade that followed, and in many ways, for decades beyond that. Let your eyes close if they haven't already. Let the images come softly. Swept silver wings, a pale, cold sky, the sharp, clean sound of a jet engine climbing. The speeds these aircraft were reaching brought new questions. How fast could a pilot go? Not the aircraft, the pilot. At the speeds jet combat now involved, the forces acting on a pilot during hard maneuvering had increased dramatically. Pulling out of a dive or turning tightly at high speed exposed pilots to gravitational forces that pressed the blood away from the brain and toward the lower body. Too many G-forces sustained for too long meant unconsciousness. And an unconscious pilot in a fast jet was not going to recover the situation. Aircraft structures, too, had to be reconsidered. The stresses of high-speed flight, of rapid maneuvers, of the vibration and pressure that came with approaching and exceeding the speed of sound, demanded engineering solutions that simply hadn't been necessary before. Metal had to be thicker in some places, differently shaped in others. Every part of the aircraft had to be rethought in light of what it was now being asked to endure. And when things went wrong at these speeds, they went wrong very quickly. A pilot who needed to leave a piston-engined aircraft in an emergency might, with effort and luck, be able to climb out and clear the aircraft. At jet speeds, that was not possible. The airflow would pin a pilot to the aircraft or destroy them the moment they entered it. The ejection seat was the answer. a rocket or explosive charge that fired a pilot still seated, clear of the aircraft in a fraction of a second. It was violent. It was hard on the body. Spinal injuries from ejections were not uncommon. But it worked. Pilots who would otherwise have had no options suddenly had one. And that one option saved thousands of lives over the decades that followed. Rest deeply now. Let your body be heavy. Alongside the ejection seat, another technology was quietly changing the nature of air defense. Radar-guided interceptors were entering service. The idea was straightforward in concept and complex in execution. An aircraft equipped with its own radar could locate an enemy aircraft in darkness or cloud cover without needing to see it. It could be guided toward a target by controllers on the ground, tracking both aircraft simultaneously. It could, eventually, launch weapons that guided themselves to the target using radar. This mattered enormously because the new threat being prepared for was not a conventional fighter. It was a bomber, high, fast, nuclear-armed. The strategic calculus of the early Cold War was built around the possibility of a bomber crossing the polar approaches and delivering an atomic weapon before it could be intercepted. The radar interceptor was the answer being developed. Aircraft like the American F-94 and later the F-101 were designed not for dogfighting, but for finding and destroying a single high-value target in any weather, at any time of day or night. They were instruments of a new kind of warfare, one where the stakes of any single failed intercept were difficult to contemplate. And at the outer edge of all of this was a barrier, a physical, real, dangerous barrier. The speed of sound, approximately 767 miles per hour at sea level, varying with altitude and temperature. As aircraft approached it, strange things happened. Controls became unpredictable. Aircraft vibrated. In some early designs, the controls actually reversed. Pilots had been lost exploring this region of flight, and for a time, the sound barrier had a reputation that suggested it might be an absolute limit. It wasn't. On the 14th of October 1947, a few years before Korea, an American test pilot named Chuck Yeager flew a rocket-powered research aircraft called the Bell X-1 and became the first person to exceed the speed of sound in level flight. He named the aircraft Glamorous Glennis after his wife. The barrier turned out to be a challenge rather than a wall. By the early 1950s, supersonic flight was becoming achievable in purpose-built military aircraft, not just specialized research machines. And the technology that made it possible, including afterburners that injected additional fuel into the exhaust stream to produce dramatic increases in thrust, was being refined and standardized. An afterburner did not make an aircraft supersonic by itself, but it provided the additional push needed to accelerate through the transonic region, that uncomfortable zone just below the speed of sound where drag peaked and control became complicated. With an afterburner lit, an aircraft could push through that region faster, more decisively, and emerge on the other side into smoother supersonic air. The roar of an afterburner igniting is one of the signature sounds of military aviation from this era onward. Loud, sudden, unmistakable. A sound that meant something was about to go very fast. That's where we rest tonight, at the edge of the supersonic. The propellers gone, the swept wings catching the light, the pilots strapped into their ejection seats, trusting the engineering, trusting the training, pushing into air that had never been pushed through quite like this before. The jet age was not just a new chapter in aviation. It was a new chapter in what human beings understood about speed and about the sky and about how much further there was still to go. Let your breathing slow now. Let the sound of jet engines fade into silence. The sky above you is quiet and deep and full of stars. Sleep gently. The story continues. Chapter 4: Cold War Giants, Bombers and Recon. After the Second World War, conflict turned quiet. The sky did not empty. It grew larger. Bombers crossed continents without landing. Reconnaissance aircraft climbed to the edge of space. Deterrence replaced direct battle. These were aircraft designed not only to fight, but to prevent war by their presence alone. Let yourself settle into the quiet. The frantic pace of wartime is behind us now. What replaced it was something stranger. A conflict measured not in battles won or lost, but in tension maintained, in presence, in the knowledge held by both sides of what the other side was capable of. The Cold War was fought in many places, but some of its most significant moments happened far above the clouds, in aircraft most people never saw and few were ever meant to know about. The logic of nuclear deterrence rested on a simple and terrible idea. If both sides possessed the ability to destroy the other, and both sides knew it, then neither side would choose to begin. The destruction was so total, so certain, so final, that rational calculation always arrived at the same answer: don't start. For that logic to hold, the weapons had to be real. They had to be survivable, and they had to be deliverable. In the early decades of the Cold War, before intercontinental ballistic missiles became the primary delivery system, the aircraft that carried that burden were the strategic bombers. Large, long-range, capable of crossing oceans and continents, and arriving over a target with a nuclear weapon. Their existence was not secret. Their existence was the point. The Boeing B-52 Stratofortress entered service in 1955. It was enormous. 8 jet engines slung beneath swept wings that flexed visibly in turbulence. A crew of several. Range measured not in hundreds, but in thousands of miles. It could take off from an American airbase, fly to a target anywhere in the Soviet Union, deliver its payload, and return. What makes the B-52 remarkable is not only what it was when it entered service, It is that it is still in service today, continuously updated, modified, re-engined, given new electronics and new weapons. The B-52 has outlasted every aircraft designed to replace it. Pilots flying B-52s in recent decades have been the grandchildren of pilots who flew them when they were new. It is one of the most enduring military aircraft ever built, and it remains operational, relevant, and capable in ways its original designers could not possibly have anticipated. Breathe slowly. Let the night be wide and still around you. There's no rush, just the long, quiet story of the sky. A bomber that can fly thousands of miles is formidable. A bomber that can refuel in the air and fly indefinitely is something else entirely. Airborne refueling, the transfer of fuel from one aircraft to another while both are in flight, have been demonstrated as far back as the 1920s. But it was the Cold War that made it a standard, essential, routine part of military aviation. Tanker aircraft, large and unglamorous and absolutely critical, orbited at designated points over oceans and continents, waiting for fighters and bombers and reconnaissance aircraft to find them, connect, and take on fuel before continuing their missions. The practical consequence was that range, which had always been one of the fundamental constraints on what an aircraft could do, became negotiable. A fighter that could fly for 2 hours without refueling could, with a tanker, fly for 4, or 6, or as long as the crew could endure. A bomber on a deterrence patrol could remain airborne for an entire day, staying aloft and ready, coming down only when its crew needed to be replaced. For a period during the most anxious years of the Cold War, American bombers carrying nuclear weapons flew continuous airborne alert. Around the clock, every day, aircraft loaded with weapons were in the air over the Arctic and the Atlantic, ensuring that no first strike could destroy all of them before they could respond. The logic was cold and precise. The reality, lived by the crews who flew those missions, was something else entirely. Let your mind drift gently, like an aircraft at altitude, high and slow and very far from the noise of things. While bombers carried the deterrence mission at high altitude and long range, another kind of aircraft was doing something quieter, and in some ways, more dangerous. The Lockheed U-2 was a reconnaissance aircraft. It carried cameras and sensors, not weapons. Its mission was to fly over territory it was not supposed to be in and see what was there. It was extraordinary in its design. Long, fragile-looking glider wings attached to a fuselage barely large enough for its pilot. A single jet engine optimized for efficiency rather than speed. It could climb to altitudes of 70,000 feet and above, where the sky above was already darkening toward black, and the curvature of the earth was visible at the edges of vision. At those altitudes, the designers believed it would be safe. Soviet interceptors could not reach it. Soviet missiles could not hit it. The U-2 would pass overhead, silent and untouchable, and come home with photographs that told American intelligence exactly what was being built, where, and how fast. For several years, that was true. And then on the first day of May 1960, a U-2 piloted by Francis Gary Powers was struck by a Soviet surface-to-air missile over the Soviet Union. Powers survived, was captured, and the incident became one of the defining diplomatic crises of the Cold War. The assumption of invulnerability had been wrong. The sky, even at the edge of space, was not safe. But if the U-2 flew high, what came after it flew faster than almost anyone thought possible. The SR-71 Blackbird was, and in many ways remains, the most remarkable aircraft ever put into regular operational service. It was designed to fly at speeds exceeding Mach 3, more than 3 times the speed of sound, at altitudes above 80,000 feet. At those speeds, the friction of the air against the aircraft's skin raised surface temperatures high enough to cause conventional aluminum to soften and fail. The SR-71 was built primarily from titanium. It looked like nothing else. Long and dark and angular, with a shape that seemed to belong more to science fiction than to an operational air force. When it flew at full speed, it was essentially impossible to intercept. Missiles launched at it could not catch it. The best response an enemy could manage was to fire a missile ahead of it and hope. The SR-71's counter tactic was simple: accelerate. It set speed records that have never been broken by a crewed air-breathing aircraft. It flew operational reconnaissance missions for decades, bringing back imagery and intelligence that no other platform could have gathered. And when it was finally retired, the people who had worked with it struggled to explain to those who hadn't quite what it had been like to be responsible for something so far beyond anything else in existence. Settle a little deeper now. Let your body be completely supported. There's nothing you need to hold up. Just rest. Not all of the innovation in this era was about going faster or higher. Some of it was about going more precisely where you needed to go. Variable sweep wings appeared on certain aircraft during this period, an elegant if mechanically complex solution to a real problem. A wing optimized for low-speed flight and takeoff needs to be shaped differently from a wing optimized for high-speed supersonic flight. Fixed wings were always a compromise between these requirements. Variable sweep wings moved. They could extend outward for slower flight, offering more lift and stability, and then sweep back sharply for high-speed operations, reducing drag and improving supersonic performance. Aircraft like the American F-11 and the later B-1 bomber used this technology, as did the Soviet Tu-160 and several others. It was ingenious. It was also heavy and mechanically demanding. Maintaining the pivot mechanisms required significant engineering effort. And as material science and aerodynamic design advanced, it became possible to design fixed wings that performed adequately across the full speed range, making the complexity of variable sweep less necessary. But for a period, those moving wings represented the best answer available to a genuinely difficult question. As aircraft grew more capable, the environment in which they operated grew more dangerous in a different way. Not from enemy aircraft alone, but from what those aircraft and the ground below them were emitting. Electronic warfare emerged as its own discipline during this era. The ability to detect an enemy's radar, to jam it, to deceive it, to understand what frequencies it operated on and exploit that knowledge, became as important as speed or maneuverability in certain contexts. Dedicated electronic warfare aircraft carried equipment designed to blind or confuse enemy air defense systems, clearing a path for strike aircraft behind them. And the weapons those aircraft carried were changing too. The gun, which had been the primary armament of fighter aircraft since the synchronization gear of the First World War, was increasingly giving way to missiles. Long-range radar-guided missiles that could engage an enemy aircraft beyond visual range. Heat-seeking missiles that could chase the thermal signature of an engine. Weapons that changed the geometry of air combat entirely, because a pilot no longer needed to maneuver behind an enemy to attack them. In theory, the beyond visual range missile made the dogfight obsolete. You found your target on radar, launched from miles away, and went home. The experience of Vietnam would complicate that theory considerably, but the direction of travel was clear. And quietly, in laboratories and design offices, something else was beginning. In the 1970s, researchers at Lockheed's secretive Skunk Works facility began working on a question that had seemed almost unanswerable. What if an aircraft could be made invisible to radar? Radar worked by emitting radio waves and detecting the energy reflected back from objects in the sky. An aircraft's shape, its materials, every surface and edge and angle contributed to its radar cross-section, the measure of how visible it was to radar detection. The work that began in the 1970s explored whether careful shaping and specialized materials could reduce that cross-section to near nothing. Whether an aircraft could pass through radar coverage without being detected, without triggering alarms, without giving the defense any opportunity to respond. The answers that emerged from that research would define the next chapter of military aviation entirely. But in the Cold War years, the work was secret. The results were classified, and the aircraft that would eventually emerge from it had not yet flown. The sky was already full of secrets. It was about to hold a few more. That's where we rest tonight, in the long, cold, extraordinary decades when the sky above us was never truly empty. When bombers circled in the darkness over oceans. When a long black aircraft was somewhere above the clouds, moving faster than sound, seeing everything. The Cold War asked the sky to hold enormous weight, and the sky held it. Let your breathing slow. Let the images soften and release. The contrails fade. The engines go quiet. Sleep gently. Chapter 5: Multirole Era, Digital Combat. By the late 20th century, aircraft were no longer just machines of speed. They became computers with wings. Mechanical cables vanished. Analog dials faded. Cockpits began to glow with digital light. Fighters could switch roles mid-flight. Data flowed invisibly through the sky. Military aviation had entered the information age. Let yourself settle. Let the weight of the day finish leaving your body. We're moving forward again into the final decades of the 20th century. The Cold War is winding toward its end. The threats are changing, and the aircraft built to meet them are changing in ways that go far deeper than shape or speed. This is the era when the cockpit became a screen, when the pilot became, in a very real sense, a systems manager as much as a flyer. From the very beginning of powered flight, the connection between a pilot and an aircraft had been direct and physical. You moved the stick, and cables and rods transmitted that movement mechanically to the control surfaces. The aircraft responded to the force of your hands and feet. It was immediate, it was intuitive, and it had limits. As aircraft became faster and more agile, those mechanical systems struggled to keep pace. At high speeds, the forces required to move control surfaces could exceed what a human pilot could physically provide. And some of the most maneuverable designs being imagined were actually aerodynamically unstable, meaning that without constant, rapid corrections, they would depart controlled flight almost immediately. No human pilot could make corrections fast enough, frequently enough, to keep them flying. Fly-by-wire changed that relationship entirely. Instead of mechanical linkages, fly-by-wire systems converted the pilot's inputs into electrical signals. Those signals were processed by computers before being passed on to the control surfaces. The computers could interpret what the pilot intended, filter out inputs that would overstress the aircraft, and add corrections of their own many times per second to maintain stability. The pilot was still flying, but the computer was translating. And that translation opened up designs and capabilities that the direct mechanical era could never have achieved. Breathe slowly. Let your thoughts settle like leaves finding the ground. Nothing urgent, nothing demanding. Inside those new aircraft, the cockpit the pilot sat in had also been reimagined. The analog cockpit of earlier generations was a landscape of individual instruments. An altimeter here, an airspeed indicator there, engine gauges arranged in their own cluster. A pilot learned to scan, moving their eyes from instrument to instrument in a practiced sequence, assembling a picture of the aircraft's state from dozens of separate readings. It worked. Generations of pilots learned it and flew by it. But it required cognitive effort. Attention divided across many separate sources of information, each of which told only part of the story. Digital displays changed the architecture of that information. A single large screen could present whatever the pilot needed most at any given moment, configured and reconfigured in flight. engine status, navigation, weapon systems, threat warnings, communications. All of it could be organized, prioritized, and displayed in ways that reduced the work of staying aware. The glass cockpit, as it came to be known, did not make flying easier in some trivially simple sense. The information available to pilots increased enormously, and managing it effectively required its own kind of skill and training. But it changed the relationship between the pilot and the aircraft systems, making it possible to process more, decide faster, and act with greater precision than the analog era had allowed. Two aircraft defined the American approach to air power in this era, and they did so in complementary ways. The F-15 Eagle entered service in the mid-1970s and was designed around a single, uncompromising purpose: air superiority. The ability to find enemy aircraft and destroy them. Everything about the F-15 was oriented toward that mission. Its radar was powerful and long-ranged. Its engines gave it a thrust-to-weight ratio that allowed it to climb almost vertically. Its maneuverability at combat speeds was exceptional. The design philosophy behind it was partly a reaction to lessons learned. Earlier aircraft had been pushed toward complexity and multi-mission capability at the expense of pure air combat performance, and had struggled in certain engagements as a result. The F-15 was a deliberate correction. Do one thing. Do it better than anything else in the sky. It was extraordinarily successful. In air combat over the following decades, in engagements over the Middle East and elsewhere, the F-15 accumulated a combat record that no other fighter of its generation came close to matching. Decades after it entered service, updated variants were still being ordered by air forces around the world. Let your eyes rest. Let the darkness behind them be soft and wide. Just here, just breathing, just listening. The F-16 Fighting Falcon arrived at roughly the same time and represented a different philosophy. Where the F-15 was large and purposeful, the F-16 was small and electric. It was one of the first operational aircraft to use fly-by-wire as a primary system, and it was designed to be intentionally unstable in certain flight regimes, because instability, carefully managed by computers, translated directly into agility. An aircraft that is always on the edge of departing controlled flight is also an aircraft that can change direction with extraordinary speed. The F-16's cockpit introduced features that became standard across later generations of fighters. The side stick controller, positioned beside the pilot's right hand rather than between the knees, was designed for use under high G-forces, when the weight of an arm pressed against a central stick might be unmanageable. The seat was reclined at an angle that helped pilots resist the blood-draining effects of hard maneuvering. Every ergonomic detail had been considered in light of what the aircraft could do to the body flying it. And unlike the F-15, the F-16 was designed from the start to be versatile. Air-to-air, air-to-ground, close air support, reconnaissance. It could carry a wide range of weapons and switch between roles with a reconfiguration of its systems. The multirole concept that would come to define the following generation of fighters was already present in the F-16's design philosophy. The weapons these aircraft carried were also changing in fundamental ways. For most of aviation history, hitting a target on the ground from the air had been a matter of physics and probability. You flew toward the target, released your bombs at the right moment, and hoped that the calculations and the conditions were in your favor. Strategic bombing in the Second World War required hundreds of aircraft dropping thousands of bombs to achieve reliable destruction of a single significant target. The inaccuracy was not a failure of effort or skill. It was a consequence of physics. Precision-guided munitions changed that equation. Weapons that could steer themselves toward a target, guided by laser designation, by television imagery, or eventually by GPS signals, turned what had been a statistical problem into something approaching a deterministic one. One aircraft, one weapon, one target. The implications were profound. Fewer aircraft needed to fly a given mission. Less ordnance was required. The risk to civilian populations near military targets decreased. And the calculus of what a small number of aircraft could achieve shifted enormously. GPS, the Global Positioning System, which became fully operational in the 1990s, extended these capabilities further. A weapon that could receive its own precise location from satellites orbiting overhead could navigate to a target with an accuracy measured in meters, regardless of weather, regardless of visibility, regardless of whether any human being was actively guiding it in the final moments of flight. The sky had become a grid, and anything located on that grid could be found and struck with a precision that previous generations would have found almost impossible to believe. Drift a little deeper now. Let the story carry you. There's nothing to figure out, nothing to solve, just the soft drift of words and the quiet dark. As the aircraft themselves grew more capable, the materials from which they were built were also evolving. Composite materials, combinations of fibers and resins engineered to be strong in specific directions, offered something metal could not easily provide: strength and stiffness without the weight penalty of aluminum or steel. Carbon fiber composites in particular allowed structures that were lighter than metal equivalents while meeting or exceeding their strength requirements. The weight saved by using composites could be spent in several ways. More fuel, extending range, more weapons or sensors, or simply a lighter, more agile aircraft that demanded less from its engines to achieve a given performance. Composites also offered advantages in manufacturing. Complex curved shapes that would have required laborious machining in metal could be laid up in composite form with greater design freedom. The smooth, carefully sculpted surfaces that became characteristic of later stealth aircraft depended partly on this freedom. And connecting all of these individual aircraft, all of these individual pilots and weapons and sensors, was something that had no physical form, but was becoming as important as any of them. data links, digital communication systems that allowed aircraft to share information with each other and with ground and naval forces in real time. One aircraft's radar could contribute to a picture being assembled from many sources simultaneously. A pilot in an F-16 could see contacts detected by an F-15 operating 100 miles away. A ground controller could push updated targeting information directly into a cockpit display without a word being spoken on the radio. The individual aircraft was becoming a node in a larger network. Its effectiveness was no longer measured only by what it could see and do by itself, but by what it could contribute to and draw from a shared operational picture. This was new, not just in degree, but in kind. Military aviation had always required coordination, but coordination through data at the speed of light, with accuracy and reliability that voice communication could never match, changed what coordination actually meant. On the ground, the way pilots were prepared for all of this was also transforming. Flight simulators had existed in simple forms since the Second World War. But the simulators of the digital era were something categorically different. High-fidelity visual systems that could reproduce the appearance of any environment. Motion platforms that provided physical feedback. Software that could model the behavior of specific aircraft types with enough accuracy that transitions from simulator to cockpit felt familiar rather than foreign. A pilot could practice emergency procedures in a simulator without risking an aircraft. They could fly missions over terrain they had never physically visited. They could face threat scenarios that would be impossible to replicate safely in actual flight training. And they could repeat those scenarios until the responses were automatic, until the body and mind had rehearsed the correct actions enough times that stress and danger would not displace them. The simulator didn't replace flight. Nothing replaced the actual experience of being in the aircraft, in the real sky, with real consequences. But it changed the economics and the safety profile of producing competent pilots dramatically. That's where we rest tonight, in the glow of digital cockpits, in the precision of guided weapons, in the invisible web of data linking aircraft across the sky. Military aviation in this era became something its earliest practitioners could barely have imagined. Not just faster or higher or more powerful, but smarter, more connected, more precise. The pilot in the cockpit was still the heart of it, but the aircraft around them had become a different kind of instrument entirely. Let your breathing slow. Let the screens go dark and quiet. The data streams fade. The sky is still. Sleep gently. Chapter 6: Stealth and Network Warfare. Then came the shape that seemed almost unreal. Sharp angles, hidden edges, surfaces designed not to be seen. Stealth changed the question from how fast an aircraft could fly to whether it could be detected at all. Visibility became vulnerability. Silence became strength. Let yourself arrive somewhere quiet. Let the day release its hold on you completely. We've traveled a long way through this story tonight, from wooden frames held together with wire, through aluminum and jets and digital cockpits, to here. This is where we are now, the present, or very nearly. The aircraft of this chapter are the ones still flying overhead. The technologies are still being developed, still being refined, still being debated. The story hasn't ended, but this is where we rest inside it. Radar won the Battle of Britain. Radar guided interceptors through the Cold War. Radar became the foundational sensing technology of military aviation, so deeply embedded in doctrine and infrastructure that the entire architecture of air defense was built around it, which meant that the most disruptive thing you could do was make radar stop working. Not by jamming it, not by flying under it or faster than it, but by designing an aircraft so carefully, so precisely, that the radio waves radar emitted simply did not bounce back in any useful way. An aircraft that presented no return, that appeared on a radar screen as nothing at all. The physics were understood before the engineering was mastered. Every surface of an aircraft reflects radar energy. The angle of each surface, the material it is made of, the edges where surfaces meet, all of these contribute to what is called the radar cross-section. A conventional fighter aircraft might have a radar cross-section comparable to a large bird. A well-designed stealth aircraft could reduce that to the equivalent of a small insect. Achieving that required a total rethinking of aircraft design. Shapes that looked nothing like anything that had flown before. Edges aligned precisely so that reflected radar energy was directed away from the source rather than back toward it. Materials that absorbed rather than reflected. Every hatch, every seam, every external fitting considered in terms of its contribution to detectability. Breathe softly. Let your body sink a little deeper. There's nothing holding you up but rest itself. The first aircraft to put these principles into operational practice was the Lockheed F-117 Nighthawk. It looked like a mistake. A collection of flat facets arranged into a roughly aircraft-shaped collection of angles and edges. It had no curves, no smooth surfaces blending gracefully into one another. From certain angles, it resembled something assembled from dark triangular tiles, each one flat and precise, and deliberately misaligned from the ones beside it. That appearance was the entire point. Curved surfaces reflect radar energy in complex, distributed ways that are difficult to control. Flat surfaces reflect it in precise, predictable directions. By carefully choosing the angles of every flat panel on the F-117, designers could ensure that radar energy striking the aircraft was reflected away from the radar receiver, back at angles that sent it uselessly into the sky or toward the ground. Not absorbed, deflected. The F-117 first flew in 1977, though its existence was not publicly acknowledged until 1988. It flew operational missions in Panama and then in the Gulf War of 1991, where it was used to strike targets in Baghdad, defended by some of the most sophisticated air defense systems then in existence. It flew at night, it flew without escort, and it arrived and departed without being engaged. It was not invulnerable. Later conflicts would demonstrate that stealth was not invisibility, and that a determined, creative adversary with the right equipment could sometimes find what stealth was designed to hide. But as an operational demonstration of what the technology could do, the F-117's early combat record was extraordinary. Where the F-117 was angular and strange, its successor in the stealth lineage was something else entirely. The B-2 Spirit looked like a dream of flight rather than a weapon. A pure flying wing, no fuselage, no tail. Just a single continuous curved surface sweeping from wingtip to wingtip, with a gentle W-shaped trailing edge. It was enormous, with a wingspan greater than a Boeing 737, and it was almost silent at altitude, the sound of its engines absorbed and dispersed by the time it reached the ground. The flying wing concept was not new. Designers had explored it since the 1940s, recognizing that a pure wing, without the drag of a fuselage and tail, offered theoretical efficiency advantages. What had prevented its operational use was the severe stability challenges it presented. A flying wing with no tail has very limited natural stability in certain axes. Managing it required either exceptional pilot skill or something the earlier era didn't have in sufficient maturity. Fly-by-wire computers, the same technology that had unlocked the F-16's agility, gave the B-2 its flyability. Computers making constant small corrections, many times per second, keeping the vast wing on course and stable in ways no pilot could achieve alone. The B-2 could carry nuclear or conventional weapons in internal bays that preserved its smooth exterior and its low radar signature. It could fly from its base in Missouri to anywhere in the world and return without landing. It was, and remains, one of the most capable and most expensive aircraft ever built. Let your mind be still, like the surface of deep water, nothing disturbing it, just depth and quiet and the soft passage of time. Internal weapons bays are worth a moment of attention on their own, because they represent one of the less obvious but genuinely important constraints that stealth imposes. A conventional fighter carries its weapons externally. Missiles hang under the wings on pylons. Bombs are mounted on racks. This is efficient and practical, allowing rapid loading and configuration for different missions. But every external weapon, every pylon, every rack, is a surface that contributes to the aircraft's radar cross-section. Hang enough weapons on a stealth aircraft, and you have largely defeated the purpose of the stealth. The solution is to carry everything inside. Weapons bays within the fuselage, sealed by doors that open only in the final moments before release and close again immediately afterward. The aircraft presents its clean, low observable exterior, until the last possible moment. The bay opens briefly, the weapon is released or launched, and the bay closes again. It works, but it limits what can be carried, requires careful design of how weapons are stored and released, and adds mechanical complexity. Every operational stealth aircraft has had to balance the requirement for internal carriage against the practical need to carry enough weapons to accomplish a mission. If stealth changed what enemies could detect, sensor fusion changed what pilots could understand. Earlier generations of aircraft carried individual sensors, a radar here, an infrared search system there, electronic warfare receivers. Each system provided its own picture, displayed on its own screen, requiring the pilot to mentally integrate multiple separate streams of information into a single, coherent understanding of the situation. Sensor fusion combined those streams automatically. The aircraft's computers took inputs from multiple sensors simultaneously, correlated them, resolved conflicts between them, and presented the pilot with a single integrated picture. Not raw radar data and raw infrared data displayed separately, but a unified representation of what was out there, assembled from everything the aircraft could sense. The F-22 Raptor and the F-35 Lightning II both incorporated advanced sensor fusion as a central design feature. A pilot in an F-35 sits at the center of a sphere of awareness that earlier pilots could not have imagined. Information from the aircraft's own sensors, from other aircraft in the formation, from ground and naval assets, all integrated and presented in a form the pilot can act on immediately. And where that information appears has also changed. Helmet-mounted displays project information directly onto the visor of the pilot's helmet. Targeting symbology, threat warnings, navigation cues, sensor imagery. All of it visible without looking at a cockpit screen, without moving the eyes away from where the pilot is already looking. The most advanced versions of this technology allow a pilot to look directly at a target and cue weapons onto it simply by looking, or to see through the aircraft itself. The cameras mounted around the aircraft's skin feeding imagery to the helmet, so that the pilot looking straight down sees the ground below as if the floor of the cockpit were transparent. These are not incremental improvements on what came before. They represent a fundamental change in the relationship between the pilot's attention and the tactical picture. The aircraft is no longer something the pilot looks at instruments to understand. It is something the pilot inhabits, surrounded by information made visible and immediate. Settle even deeper now. Let the words come and go like breath. You don't need to hold any of it. Just let it drift through, soft and slow. The modern fighter is also, in a very real sense, a flying computer network. Data links that were a new capability in the 1990s are now fundamental infrastructure. An F-35 operating in a contested environment is continuously sharing what it sees with every other platform in the network and receiving what they see in return. Its radar might operate in passive modes that don't emit detectable signals, because it can receive targeting data from other aircraft that have already located the threat. The network sees more than any single aircraft could see alone, and every aircraft in the network benefits. This has changed the way air forces think about individual aircraft. A single F-35 is capable. A formation of F-35s, sharing sensor data and coordinating through data links, is qualitatively different from 4 times a single aircraft. The whole is considerably more than the sum of its parts, in ways that earlier aviation never had to account for. Beyond the crewed aircraft, the sky has been filling with something else. Unmanned aerial vehicles. From small reconnaissance drones to large armed platforms capable of long-endurance missions, have expanded enormously in capability and prevalence over the past 2 decades. They can loiter over an area for hours or days, something no crewed aircraft can practically achieve. They can operate in environments too dangerous or too contested for a crewed aircraft to survive. They remove the pilot from the equation of acceptable risk in certain missions. The relationship between crewed and uncrewed aviation is still being worked out, still evolving, and will almost certainly look very different in another decade than it does today. What is already clear is that the unmanned aircraft is not a replacement for the crewed fighter, but a complement to it, another node in the network, another source of information and capability that the overall system can draw on. And at the edge of what is currently possible, research continues into something that makes even supersonic flight seem almost leisurely. Hypersonic flight. Speeds above Mach 5 times the speed of sound. At those speeds, the physics of flight change in fundamental ways. Conventional aerodynamic surfaces lose effectiveness. The heat generated by air friction becomes extreme enough to challenge every material currently used in aircraft construction. The time available for detection and response shrinks towards zero. Several nations are actively developing hypersonic weapons and, more ambitiously, hypersonic aircraft. The challenges are significant. The progress is real. What emerges from this research in the coming decades will define the next chapter of a story that began with wood and wire over the fields of France. That's where we come to rest tonight. At the edge of what is known and the beginning of what is coming. Think of everything this story has held. The reconnaissance pilots of 1914, peering over the side of open cockpits at the trenches below. The fighter pilots of the Second World War, fighting in aluminum machines with engines that roared. The jet pilots chasing the sound barrier. The crews of bombers circling in darkness over the Arctic. The digital cockpits of the multirole era. And now, aircraft that cannot be seen. Pilots wearing the sky on their visors. Networks of machines sharing a picture of the battlefield that no single set of eyes could ever assemble alone. It is an extraordinary story, and it is not finished. Let your breathing slow now. Let the angular shapes and the dark surfaces and the invisible data streams all soften into quiet. The sky above you is still. Whatever is up there tonight is moving too high and too quietly to hear. Rest now. The story has brought you here, to the present, to this moment, to the simple and sufficient act of being still and breathing and letting sleep come. It will come. Chapter 7: Emerging Trends and the Future. Now, the sky is evolving again. Pilots share the air with drones. Algorithms assist decisions. Aircraft communicate in quiet digital networks. Some fly faster than ever imagined. Others fly without a human on board at all. The story of military aviation is still unfolding, and the horizon remains wide. Let yourself settle into the quiet one more time. We've come a long way together through this story. From grass strips in France to supersonic jets. From open cockpits to digital visors. From reconnaissance by eyesight to networks of sensors spanning the sky. Tonight, we arrive at the final chapter. Not the end of the story, because the story has no end yet, but the edge of what is known, the place where the present becomes the future, and certainty gives way to possibility. Rest here gently. This is where things get interesting, in a different way. For as long as military aviation has existed, the aircraft and the pilot have been inseparable. One without the other was incomplete. The pilot gave the aircraft judgment, adaptability, the ability to respond to the unexpected. The aircraft gave the pilot reach, speed, and capability no human body could achieve alone. That relationship is not ending, but it is changing. The loyal wingman concept sits at the center of that change. The idea is straightforward in outline, though the execution is anything but. A crewed fighter, flown by a human pilot, operates alongside one or more unmanned aircraft. The unmanned aircraft are not simply remote-controlled drones following orders. They are capable, semi-autonomous platforms that can sense, reason within defined parameters, and act. They can fly ahead into the most dangerous airspace. They can carry weapons or sensors or jamming equipment. They can absorb risk that would otherwise fall on the crewed aircraft and the human being inside it. Several nations are actively testing loyal wingman concepts. The Australian-developed Boeing MQ-28 Ghost Bat is among the most prominent. The United States Air Force has been developing its own collaborative combat aircraft program. The design philosophy varies, but the underlying intent is consistent. Extend what a single crewed aircraft can do by surrounding it with capable unmanned partners that multiply its reach and reduce its exposure. What this means in practice is still being worked out. The relationship between pilot and wingman drone, the division of decision-making between human judgment and machine capability, the rules of engagement that govern when an autonomous aircraft can act without explicit human instruction. All of these are open and serious questions that go beyond engineering. into ethics and law, and the nature of accountability in conflict. Breathe slowly. Let your thoughts settle. These are big questions, and tonight they don't need answers. Just awareness. Just the quiet recognition that the sky is still full of new things. Artificial intelligence has entered the cockpit, not as a replacement for the pilot, but as a presence alongside them. In earlier generations, the computer in an aircraft was a tool. It did what it was told, quickly and accurately, but within narrowly defined parameters. The pilot commanded, the computer executed. The emerging relationship is more nuanced. AI systems can now process sensor data, identify threats, propose courses of action, and manage certain tasks autonomously, at speeds and with a consistency that human cognition cannot match. A pilot facing a complex threat environment, managing multiple systems, tracking several contacts simultaneously, making targeting decisions under time pressure, can be assisted by an AI that has already done much of the pattern recognition and filtering, presenting a cleaner, more actionable picture. In 2020, an AI system developed by DARPA defeated experienced human fighter pilots in simulated air combat, with a record that surprised even its developers. The simulation was constrained, and the implications for real combat are complex, but the result was noted across the aviation world. The question of what AI can and should do in the cockpit, and how much authority it should be given, is one of the defining conversations of this era. The priority, consistently stated across the air forces developing these systems, is reducing pilot workload, not replacing pilot judgment, but freeing the pilot to exercise judgment on the things that matter most, by handling the things that don't require human decision-making at all. Let your mind soften, like a light slowly dimming, comfortable, easy, just here. The propulsion systems that power military aircraft are also being reimagined, though more gradually than some of the other changes underway. Electric propulsion, which has transformed civilian aviation at the smaller end of the scale, is being studied for military applications. The challenges are significant. Energy density, the amount of energy a battery can store relative to its weight, remains far below what liquid fuel provides. A jet engine burning kerosene carries its energy source in a form that is extraordinarily compact for the power it releases. Batteries cannot yet compete at the scale military aircraft require. But the research continues, driven partly by the operational advantages electric propulsion could offer. An electric motor is quiet. It produces no heat signature from combustion. It requires less maintenance than a turbine engine. For certain unmanned platforms, operating at lower speeds and altitudes, these advantages are already becoming practical. The military aircraft of the near future will almost certainly be hybrid in their approach, combining conventional propulsion for performance-critical phases of flight with electric systems for stealth, efficiency, or specific operational requirements. The all-electric fighter remains distant. The electrically assisted military aircraft is already closer than many realize. At the other end of the energy spectrum, research into directed energy weapons is advancing toward operational capability. A directed energy weapon, in its most practical current form, is a high-powered laser. Instead of firing a projectile, it fires a concentrated beam of light that delivers energy to a target fast enough to heat and destroy it. The advantages over conventional weapons are significant in certain contexts. The beam travels at the speed of light. It costs almost nothing per shot compared to a missile. It can be fired repeatedly as long as power is available. The challenges are also significant. Atmospheric effects, dust, humidity, turbulence can scatter or attenuate a laser beam. The power systems required for militarily useful energy levels are large and heavy. Targeting a fast-moving aircraft or missile with enough precision to deliver damaging energy requires exceptional accuracy. Progress is real, however, and the systems being tested today are more capable than those tested a decade ago. Directed energy weapons are already deployed on certain naval vessels for defense against drones and small boats. Their extension to airborne platforms is a matter of engineering and power management, not fundamental physics. Drift a little deeper now. The future doesn't need to be held or understood tonight. Just let it rest at the edges of awareness, gentle and open. The surfaces of stealth aircraft, which were already carefully engineered in the F-117 and B-2 era, continue to evolve. Early stealth coatings were effective but demanding. They required extensive maintenance, were sensitive to moisture and temperature, and added significant time and cost to keeping aircraft operational. The coatings used on the F-22 and F-35 are more durable and easier to maintain than those of the earlier generation. But the work of making stealth practically sustainable in operational conditions continues. New materials and application methods are being developed that could make low observable surfaces more robust, more effective across a wider range of radar frequencies, and less labor-intensive to maintain. The stealth aircraft of the next generation will likely be less detectable than those flying today, while being easier to keep in the field. Alongside coatings, the broader concept of low observability continues to expand beyond radar signature to include acoustic signature, thermal signature, and electromagnetic emissions. An aircraft that is invisible to radar, but loud, hot, and broadcasting strongly on multiple frequencies is only partially hidden. True low observability requires managing all of these dimensions simultaneously. The way aircraft are designed and developed is also being transformed by technology that never leaves the ground. A digital twin is a precise computational model of a physical system, detailed enough that what happens to the model accurately predicts what would happen to the real thing. For aircraft development, this means that designs can be tested, stressed, modified, and refined in software before a single physical component is manufactured. Structural failures can be identified and corrected in the digital model rather than in a prototype. Maintenance schedules can be informed by the digital twin's model of component wear, predicting failures before they occur. The development cycle for new aircraft has historically been measured in decades and cost billions before a flyable prototype existed. Digital twin technology, combined with advances in simulation and computing power, is beginning to compress that cycle. Not to eliminate the need for physical testing, which remains essential, but to arrive at physical testing with designs that are already more mature and less likely to require fundamental revision. The next generation of military aircraft will have been flown thousands of times in simulation before they fly once in reality. The pilots who eventually fly them will have accumulated hours in those same simulations. The boundary between the virtual and the physical in military aviation development is becoming more permeable every year. And underlying all of it, the software. Modern military aircraft are, in a profound sense, software platforms. The hardware, the airframe and engines and physical sensors provides the capability. The software determines what that capability can do and how it can be used. An F-35 that receives a software update is, in meaningful ways, a different aircraft from what it was before the update. New weapons can be integrated, new sensor modes enabled, new tactics made possible. This means that the development of a military aircraft no longer ends when the last airframe rolls off the production line. It continues for the entire service life of the platform, through a continuous process of software refinement and capability addition. The aircraft flying today will be more capable in 5 years than they are now. Not because they have been physically rebuilt, but because the software that defines their behavior will have evolved. It is a different model of capability from anything that existed before the digital era, and it is one that creates both opportunities and vulnerabilities that the aviation world is still learning to manage. That's where we come to rest, at the edge of what is known and the beginning of what is being built. The loyal wingmen being tested today, the AI learning to see the sky, the directed energy weapons inching toward operational readiness, the digital twins flying aircraft that haven't been built yet, the coatings becoming quieter, more durable, more invisible, the software that never stops being written. Military aviation has always been a conversation between human ambition and physical possibility, between what the sky demands and what engineers can provide. That conversation began with Otto Lilienthal gliding off hillsides in Germany in the 1890s. It passed through the fields of France and the skies over Britain and the frozen approaches to the Arctic and the digital cockpits of the multirole era. It hasn't stopped. The sky is still out there, wide and deep and full of things not yet imagined. And somewhere, in a laboratory or a design office or a test facility in a desert, the next chapter is already being written. Let your breathing slow now. Let the images soften. The drones returning to base. The screens going dark. the aircraft settling into their hangars, quiet and still. The story has carried you a long way tonight, from the very beginning to the very edge of now. You don't need to hold any of it. It will be here when you return. For now, just this: the quiet, the stillness, the simple fact of rest. Sleep well. You've earned it. Good night.